Okay. This is our 12th section about electromagnetic for ELECO, about electromagnetic theory. And we have 5 presentation. For this reason, we have to be careful about the duration of your presentations, because before that, one speaker has spent a lot of time. Okay. Also, if you have any question, please send a chat. I can see your chats. Okay, our first presentation is implementation of FMCW radar by using SDR. And that is given by Serdar Kaya from Baskent University. Okay.
May I begin?
Serdar, can you share your presentation, please?
Yes.
Yes, we are hearing your voice. Locate the presentation and share. Yes, that's okay. Thank you very much.
Okay. So hi everyone. My name is Serdar Kaya. I'm from Baskent University, and today I will be presenting the paper titled as Implementation of FMCW radar by using SDR. Me and my colleagues, Dr. Alparslan, Yapici, Berk, Tibikoglu, and Serif, Onurcan, Yazici, prepared this paper. Before I get into the presentation, allow me to give you a little briefing about the contents. First, I'm going to give you an overview about the radar systems and FMCW radars and talk about theory. After that, I'm going to talk about the aim of the study and give you a little overview of the SDRs and their benefits. After that, I'm going to talk about the hardware we used in the study and talk about the system and software structure offered and delivered. And then I'm going to talk about the systems and give the specifications of the system. And right after that, I'm going to talk about the internal design we made in this study. And right after that, I'm going to talk about the experiments and trials done. And after that, I'm going to give you a conclusion regarding the results we've gathered. And then I'm going to do the presentation references. So let's start with radar systems. As most of you know, the word radar stands for radio detecting and ranging, which simply implies that the system's capability of measuring surrounding objects, range and velocity values by simply radiating radio waves and simply getting the echoed or simply processing the received or echoed signals. There are 2 main types of radar signals. First one is pulse radars. They use simply one source or one antenna for transmitting and receiving at the same time. They're mostly prepared for high power applications where the system needs to cover a large area or etc. And we have continuous wave radars. Continuous wave radars simply use multiple sources or at least 2 antennas. Of course, if you're using antenna array, the number can be increased. They use at least 2 different sources for transmitting and receiving, and they continuously send the wave through the environment. There are 2 main types of it. First one is unmodulated continuous wave radars, where a system is simply radiating an unmodulated normal radio wave. It is able to measure things like velocity, but when it comes to measuring time of flight or range information, it has this disadvantage. And we have modulated continuous wave radars, which is also part of our study, where the system simply radiates a modulated continuous wave, which allows it to have a reference within the sense signal, so it can have other measurements like time of flight, and you can get the range information easily. And FMCW radar, word FMCW stands for frequency modulated continuous wave radar. This type of radar is sending frequency modulated continuous waveform through the environment. The type of waveform can be changed, it can be triangular, it can be sawtooth, and this type of frequency modulated continuous waveforms that value changing with time is called chirp signals. And since it has its own reference within the signal, it allows us to measure both range and velocity. And since we are using 2 different sources, we don't have to wait for our signal to be transmitted in order to start receiving. So we have minimum range advantages. And in order to have a little more understanding about the FMCW radar system, let's examine the picture. We have a red waveform, which simply implies the transmitted waveform, and the blue one, which implies the received waveform, and delta F, which is known as beat frequency, is the frequency difference between those signals. This beat frequency simply hides the time of flight data and therefore the range information, which we need to have. In order to have this delta F or beat frequency, we need to simply mix two signals. It can be done with digital or analog structures. This type of mixing is also called chirping, and the range information from delta F can easily be calculated by first formula, where C stands for speed of light, and S stands for sleep time, which is the period of the chirp signal. And one of the most important parameters in the FMCW radars is range resolution, which can be calculated with the second formula, where B stands for bandwidth. But we must note that this the derivation of this formula comes from the assumption that number of samples for the FFP is equal to the samples that can be gathered in the sweep time. So if we simply neglect that, we can simply calculate the range resolution by the FFP resolution formula, which is given in the third part, where FS stands for sampling rate and NS stands for number of FFP points. So if we simply improve the number of samples gathered by using FFP zero padding type of signal processing based approaches, which we will be using in this study, we can simply improve range resolution theoretically. But we must note that using zero padded FFP might cause spectral leakage, and therefore it will cause a spectral growth. And it can be reduced by windowing, which we will be using in the study. But since if we have more than one echo signals, the interference between those signals would get pretty high. So this type of signal processing technique would be useful if there's a single target within the environment to simply look for. And our aim is to develop an FMCW radar that is capable of detecting single target with sufficient amount of range resolution. The SDR we will be using is analog device Erdem Pluto, which is a low-cost SDR compared to the other SDRs that are used to simply implement the same design like USRPs or GNU-based devices. In order to overcome the technical difficulties, a signal processing-based design approach will be proposed. And before I get into the hardware, allow me to tell you a few words about software-defined radios or SDRs. They simply are devices or structures that enables us to realize most of their functions by making simple software configurations. They mostly consist of two main parts, digital and analog or RF parts. As you can see in the image, this is analog device Erdem Pluto's inner structure, which contains a Xilinx link and an ADI AD9363 RF chip. They're very easy to configure by computers, like you can use HDL or Simulink, which we will be using in the study, which I will mention in the following slides. And the hardware specifications, the analog device Erdem Pluto SDRs, technical specifications you can see in this slide. The most important parameters we will focus on is frequency range, which changes from 325 megahertz to 3,800 megahertz. The ADC-DAC sampling rate can get up to 61.44 megasamples per second. Yet, since we're going to do the mixing process or the chirping process in digital part, we need system to be working with losing no samples at all. So the maximum value, maximum sampling rate we could get with this SDR was 2 megasamples per second. So that would be our maximum. And the bandwidth can get up to 56 megahertz, but since we're going to be able to use only 2 megasamples per second of sampling rate, thanks to the complex sampling, the bandwidth will be only equal to 2 megahertz. The power output is around 7 dBms, noise figure is low at 3.5 dBs, and resolution and impedance value is around 50 ohms. The resolution is 12 bits. And as the antennas, as I said, since we're going to be preparing a continuous wave radar, we're going to need at least 2 antennas, one for transmitting and one for receiving. And we needed a directional antenna in order to focus our system to a specific location. So we chose antennas or circular waveguide antennas. We chose them because they're very low cost and easy to design and build. You can simply implement your design by using different structures like Pringles can or normal food can, which we also use, and you will see in the following slides. And give you an overview about system structure. In the hardware, we're going to use an Erdem Pluto SDR, 2 antennas, and a computer for SDR configuration and signal processing. And the software we will be using within the computer is MATLAB Simulink R228 with communications toolbox support package for an Erdem Pluto radio. And as you can see in the system structure, the SDR stands in the middle, which has an FPGA in our front-end part, which simply takes a synthesized digital chirp signal or signal that will be sent to the environment, and it will convert it, turn into an RF signal and send it to the environment. After that, it will receive the signal and digitize it and turn it back to the computer for its process over FFT-based DSP algorithm. And the software structure, which is the most important part of the study, is as follows. After we take the digital input from an input or radio, we will put it into a buffer. The buffer will simply overlap the samples and add it, which is known as coherent pulse integration. And by that way, we will not have any increasing in sample numbers. After that, we will make a digital dechirping process or mixing process in order to get the beat frequency. Right after that, we will have the windowing process, which we will be using hand window in it in order to overcome the spectral leakage problems. And after that, we will make a zero-padded FFT. And right after that, we will be using a peak detector algorithm, which will be fine-paced from MATLAB to detect the output. And the system design, as you can see, we have an operating frequency of 2 gigahertz. Bandwidth, as we're using maximum, is equal to 2 megahertz. The maximum range, since we're going to use all the available power from the SDR, will be equal to 280 meters. And a range resolution, since the bandwidth only is able to offer 75 meters, and with this signal processing-based approach, we're planning to get a theoretical range resolution around 1.46 meters. The read period is around 8 milliseconds, which is 5.5 times higher than the time of flight maximum range offers. ADCDA sampling rate is equal to 2 megahertz. The number of FFT points is 8,196, which enables us to have the theoretical range resolution of 1.46 meters. And the buffer size is 8 sweeps. We simply gathered it from the field experiments we've made from the SDR. And the antenna design, as I said, we will be designing 2 circular waveguide antennas. These waveguide antennas will have the following physical dimensions. We calculated it by using MATLAB and other online tools. And one of the most important analysis we needed to make with the antenna is alpha beamwidth analysis, since it simply shows us how much we can focus our system into a specific location. And as you can see, at 2 gigahertz, it is around 95 degrees. We must say that as the range or distance increasing, the number of the field coverage of the antenna will get pretty high, and therefore, since it's not pretty, we are not pretty able to simply downgrade it by making changes with the antenna design. We simply adjusted our measurement according to it, which I will be referring in later slides. And the realization of the antennas, as you can see in the image, this is the final image of the antennas after the production. And the final appearance of the system, as you can see, we have 2 antennas, one for transmitting, one for receiving, and they're connected to the SDR, and SDR is connected to the computer. And the test environment, you can see we have a metal lamp as a target. And allow me to tell the viewers about the measurement, since we have a high power beamwidth and a very high range resolution, which is around 75 meters. Since we're planning to download it around 1.46 meters, it's pretty high, and we don't know where it would stop. So we thought it would be the best to simply measure the frequency bin change, the distance where frequency bin change happens, which would simply imply detection of a range change, which would simply imply the resolution that our system can offer. And the results, as you can see, within 7.7 meters of real distance, we saw frequency bin change. Frequency bin change simply shows us a 1.46 meters of measured distance. It is pretty normal, since we have simply adjusted the number of FFT points to be equal to simply have an interval of 1.46 meters in the spectrum. And after the trial, the system was found to be sensitive around 7.7 meters. Although this is a lot worse than theoretical value of 1.46 meters, if you compare it to 75 meters of band of the range resolution, which the bandwidth had to offer, we have made it pretty good progress. But it should be noted that the results could be affected from surrounding obstacles or multiplied effects. Since we have a high power unit of the antenna, the interferers would also be affected. And as a result, we can say that despite low bandwidth and other technical challenges, a low-cost system with significant amount of resolution was created by using signal processing techniques, and the results are also promising and can be used as a guidance for creating such systems for specific scenarios. And in that case, our scenario was having a singular target to detect in the environment. These are the references. And thank you for your time. If you have questions, I'll please answer them.
Okay. Okay. Is there any question about this presentation? Okay. Especially your antenna is very interesting for me. Did you recognize any dependency or change due to multiple reflection?
Well, we are completely sure that the system
Multiple
can get affected from it since it has high power beamwidth, but we're certain about the results since after multiple trials, the results were same. Of course, an anechoic chamber would be pretty sufficient for us to measure the actual results. It would be good measurement type, but since we didn't have that advantage, and that was the best type we could ever measure.
Okay. Okay. Thank you very much for your very good presentation.
Thank you.
Second presentation about name is a hybrid simulation model for characterization of nonlinear circuits using harmonic radar. And I hope that it will be presented by Yucel Tatak. Okay?
Yes.
Mr. Yucel, can you put your presentation on your screen and then share to us? Yes, we are seeing.
Okay. First of all, welcome to all, and thank you for attending this session, for listening to simulation, listening to my presentation. The title of the presentation is a hybrid simulation model for characterization of nonlinear circuits using harmonic radar. We prepared this study with Harun, Taha, Hayvacı, and Imam Yazici from top University of Economy and Technology. First, I want to introduce you the outline of my presentation. In the first 2-3 slides, I will give a brief introduction, then introduce you the antenna models designed in HFSS for harmonic radar simulations. In the third part, circuit simulations in ADS using HFSS free space radiation data and generation of characterization curves will be presented. Two-tone excitation for harmonic radar will be introduced, and finally planned future works and some concluding remarks will be given. This is the basic diagram of an harmonic radar. Different from other traditional linear radars, harmonic radar transmits a signal at frequency F1, F2, and F3, and receives frequencies not at F1, F2, and F3, usually at target generated frequencies FA, FB, and FC. These FA, FB, and FC are harmonics of maybe harmonics of the transmitted frequencies or the intermodulation products of the transmitted frequencies. The target is usually the nonlinear components in the target are the source of these nonlinearities, and the operating principles of harmonic radar usually relies on the nonlinearities in the targets. Here in the graph, we can see that linear response usually from a target starts from a higher level than nonlinear response, because nonlinear products have lower power values than the linear scatterers from the targets. As I mentioned, nonlinear radar is usually used for detecting electronic targets, has the advantage of high clutter rejections because most of the clutter reflects at the transmitted same frequency of the transmitted frequency. Nonlinear targets may be modeled by a power series with power series expansion with, Nonlinear targets may be modeled by a power series with complex polynomial coefficients. The transmitted signal is an incident. It has a complex, it has an amplitude, and it has a frequency omega 0 and the initial phase 0, T0. The reflected signal has a coefficient of an. This is the complex coefficient, and the It is actually the output of this study. Aim of our study is to obtain these AM coefficients. Here N stands for the harmonic number. A variety of waveforms may be transmitted, for example, 1 tone and 2 tones simultaneously at the same time. Variety of signatures may be collected. As I mentioned in the first slide, we can detect harmonics of the transmitted frequency, or if we transmit 2 tone, we can get intermodulation of the 2 frequencies. There are some examples in the literature that works on harmonic radar, usually used for insect tracking by using conformal tags. May be used for vulnerable road users, for automotive radars, for detecting vital signs from some patients or other living ones. And another notice is that metal surfaces usually reflects the third harmonic rather than the second harmonic. Nonlinear circuits usually reflects, it is easier to detect nonlinear circuits at the second harmonic, but metal surfaces usually reflects at third harmonic. As I mentioned, the harmonic radar has advantages, but it also has some disadvantages. As the power level return from target is too low, it is necessary to transmit high power levels to drive the circuits into nonlinear region and get that nonlinear characteristic. Received waveform, unlike linear radar, is not a linear sum of the device responses. Received powers also usually very weak compared with the transmitted probe signals. So this requires implementation of very sensitive receivers and detection of very low noise power levels. Antenna modules designed in HFSS. In this study, we tried to build a setup. The transmitter, our radar has a transmit antenna and a receive antenna. On the circuits, we modeled 2 antennas, as one antenna as opportunity receive antenna and other antenna for opportunity transmitter antenna. For the receiver antenna on electronic circuit, we modeled a simple dipole antenna tuned to fundamental frequency. Here, our fundamental frequency is 1 GHz. Similarly, for transmitter antennas, the circuit, radar transmitter signal is captured by the circuit. It is fed through the circuit, and harmonics are generated. The generated harmonics are re-radiated from this log periodic dipole antenna, and it has resonant frequencies. It has good return loss. Compared, it is adjusted such that it has good return loss at harmonic frequencies. TX and RX antennas for harmonic radar or harmonic detector is a Vivaldi antenna. This antenna transmits at 1 GHz and will collect data up to 5 GHz. So it should be a very wideband antenna, and the transmit and harmonic frequency S1 ones are given in the figure. The final model is shown as below. As I mentioned, the port 1 is the radar transmitter antenna. The port 2 is the radar receiver antenna. Port 3 and port 4 are the opportunity antennas model for the electronic circuit. The electronic circuit will be inserted in this port 3 and port 4. That part is, this simulation is conducted in HFSS. This free space radiation data is collected, and it is inserted into ADS as this black box S4P. We have 4 ports. Some nonlinear circuits are modeled in ADS using free space data from HFSS. The input power to the transmit port is swept from 0 dBm to 40 dBm to observe the nonlinear characteristics of the circuits. harmonic balance simulation tool of the ADS is used. A fundamental tone and next four harmonics are observed from simulations. This is the first circuit, diode limiter circuit. As I mentioned, circuit here, the transmitter power is port 1 to the port 1 of the radar. Output is the second port, and the circuit is connected to the third and fourth ports. The characteristics of the circuit is obtained. These are the nonlinear responses of the circuit. They have some nonlinearities in the characteristics, as you can observe. Similarly, for the diode clamper circuit, we modeled the same similar circuit, and for full wave rectifier circuit, again, we get harmonic power curves. In addition to single-tone excitation, it is possible to also excite the circuit using two-tone excitation. In this case, we use two frequencies very close to each other, 1 GHz and 1.1 GHz here. And it causes at harmonics 2 GHz and 1 and 9 GHz and the intermodulation products. These are the intermodulation products. Same curves can be obtained for these intermodulation products also. Also for other two circuits, the same procedure is also used. After that, the planned future work is as follows: classification of these circuits using statistical properties of harmonic curves like mean, skewness, and variance. As I showed you the statistical curves, this curves has some statistical characteristics which is specific to the circuit, and using these specifications, these characteristics, we study on the classification of the circuits. Also, this is just the continuous wave signals are used here, and it is possible to add some clutter and noise to the system and investigate the noise of this, the effect of these disturbances. Finally, investigate the effect of the electric materials and obstacles between transmitter and circuit ports. In the free space part, it is HFSS here. We can model some dielectric components and some obstacles between radar target and the circuit ports to see the effect of these obstacles and modify our design accordingly. This is all for my presentation. If you have any questions, I would love to answer. Thank you.
Thank you very much. Do you have any questions? Okay, can I ask a simple question?
Of course.
I hope you have a very, very sensitive type equipments in order to record or measure the harmonics. Also, is it easy to separate the intermodulation of these harmonics? Is it easy?
Intermodulation of this...
Possible intermodulation.
Actually...
Harmonics with each other.
Intermodulation of harmonics, you mean, right?
Because there's a possibility. Harmonics, for example.
Actually, there is a possibility of
mixing the signals.
As we transmit to high power levels from the transmitter and receiver, the receiver side also has some internal reflections. As I mean, the detection circuit has also self-generated harmonics and self-generated this nonlinear harmonics, and we use some sensitive filters, some narrow band filters to filter out them. In the literature also there are some...
You have to use. Yes, you have to use.
No, not yet, but in the literature there are some, and
okay.
Some simulations we conduct.
Okay. Thank you very much for your good presentation.
Okay, thank you.
Thank you. Next one. The effect of amplification in microwave-based quantum radar systems. This presentation will be given by Murat KARAKOC. I hope so. Murat,
yes, I am here.
can you put your...
Can you see my screen?
Please. Yes, now, but a few minutes. Yes, we are seeing.
I am Murat from Ankara Yıldırım-Beyazıt University, Electrical Engineering Department. I worked with Ozgun and Behzat Hoca in this study, which is about amplification effect in microwave-based quantum radar systems. This is my outline. It will start with introduction part as usual. Then I will give you information about quantum radar systems. And the following part, we will observe the simulation results. Last but not least, some comments in our simulation. Finally, you can see our references. Quantum physics related to the behavior of matter and light on the atomic and subatomic size. When two physical systems are entangled, these systems have strong correlations with whatever distance between them. We assume that these systems, which you see in the picture, are entangled. Then, for instance, if we know the direction of the polarization is upward, we directly say that another one is a downward direction. Quantum radar concept is rather similar to classical radar, but either part is included in quantum radar, as you see in the bottom of the picture. Quantum radar research started with the St. Lloyd's seminal paper from MIT, named as Enhanced Sensitivity of Photodetection via Quantum Illumination. Then it is followed by quantum illumination with Gaussian states in the same group from MIT. And in 2009, Guha and Erkman studied on the optimum receiver for target detection. As I said in the introduction part, essential part of quantum radar is entanglement generation, in which we have three methods for this. The first method is a spontaneous parametric down conversion, where, as you can see in the picture, by using a nonlinear crystal called as a beta-barium borate, two lower energy photons are produced, which are entangled to each other. The second method was proposed by Shabir Barzanjeh from Aachen University in 2015, in which, with the help of mechanical resonator and optical cavity, optical signal converted to microwave. After reflection from a target, the received signal converts to the optical signal. In the last method, David Long and his colleague from University of Waterloo generate entangled microwave signal using Josephson parametric amplifier near to the absolute temperature. In this picture, Josephson parametric amplifier mounted on a PCB. For the generation of two-mode squeezed vacuum signal, superconducting quantum interference device and cavity resonator have been utilized. Firstly, you can see the experimental setup, and then I will show you the internal structure of this setup, actually how entangled signal is generated. In the left-hand side, you can see the general block diagram of this group microwave-based radar system. Shot noise, tuned junction, and bias T is used for calibration process. To confirm that JPA signal is entangled. As you can see, both calibration and JPA units are structured in dilution refrigerator, approximately 7 millikelvin. This signal then amplified, transmitted, received consecutively. In the upper right-hand side, you can see the internal structure of the Josephson parametric amplifier. Phi T refers to the pump signal indicated in the bottom FP. By applying external magnetic field in the frequency FP, with the help of cavity resonator, we can generate Fs and Fi. I mean an idler signal. In order to see the amplification effect in microwave quantum radar, we use a covariance matrix structure for the signal and idler mode, in which I and Q refer to the in-phase and quadrature components respectively. In here, diagonal elements show the correlation between in-phase and quadrature, while main diagonal shows the power of signal and idler modes. In the following matrix, you can see phase-sensitive covariance matrix structure, different than phase-insensitive amplifier, in which both I and Q components are amplified with the same order. In contrast, phase-sensitive amplification, I and Q amplification coefficients are inversely proportional to each other, meaning that when we increase the gain of the in-phase component of the signal, we decrease the gain of the quadrature component in the same order. This amplification method protects the entanglement between signal and idler mode. We get the following simulation results, in which we increase both signal and idler mode in the same order, referred to as a symmetric amplification. In other case, signal and idler are amplified different order, called as an asymmetric amplification. In here, rho equals to 0, which means that there is no target in our range. For rho equals to 0.04, reflection from a target is very low. For rho equals to 0.4, there is a good reflection. Rho should be between 0 and 1. You can see the amplification effect on the mean and variance clearly in this table. To sum up, 3 amplification cases have been investigated in this study. Since amplification has a potential to destroy entanglement, it is quite important for quantum radar systems. These are our references. Thank you for attention. Any questions?
Okay, thank you very much. Do you have any question? Okay. I hope also you have to find very, very sensitive type measuring devices. It is not easy to do this type of implementation. I hope so. Okay, thank you very much for your useful and good presentation. Thank you very much. Okay, the next presentation. Okay, thank you. The next presentation is a Yucel power combiner with 20 watt wideband isolation termination and 25% fractional bandwidth. This will be presented by Rabia Tuylek. Is it okay? Can you open your microphone, please?
Okay.
Okay, thank you.
Hello to everyone. I'm Rabia Tuylek. I'm fourth year student at the Department of Physics Engineering at Istanbul Technical University. Today I will give you a presentation about the Yucel power divider circuit we designed for high power application. If I talk about the contents, respectively, power divider combiners, Wilkinson power divider or combiner, insulation resistant layout problem, Yucel power divider or combiner, why Yucel power divider, Yucel power divider circuit design, simulation of these circuits, production and laboratory measurements. Aim of this project, in order to reduce the spread of the COVID-19 coded virus, it's planned to design and implement 30 dB gain power amplifiers with 500 watt output power in the 2.4 and 2.5 gigahertz bands and 10 watts output power in the 7 and 8 gigahertz bands. For this, it's planned to use power divider circuits. It will be analyzed how much the energy given to the infected surface at the specified frequencies under special laboratory conditions with a suitable antenna affects the viability of the virus. It has three applications. These Yucel power divider, Wilkinson power divider, insulation resistant layout problem. As a first step, a power amplifier with 20 watts output power in the 2.2 and 2.8 gigahertz bands is designed. This is accomplished using the Yucel power combiner circuit design. Power dividers and combiners are used as attenuators, phase shifters, mixers, amplifiers, modulators, broadcast shaping circuits in antenna systems in base centers, wireless communication devices, signal processing applications, RF and microwave integrated circuits. Here are the must-haves in a power divider circuit. The power supplied to the input should be divided into n output ports in the desired ratio, and input gate impedance to source impedance. The impedance of the output gates must be matched to the load impedances, and when one of the output ports is powered, the other output ports must not have power output. There are different power divider and combiner circuits depending on the type of application to be used. Yucel and Wilkinson power dividers are generally used in high power division. Import factors in RF and microwave power dividers: bandwidth, insertion loss, insulation, power split, phase balance, power capacity, return loss, amplitude balance. Now, Wilkinson power divider. The Wilkinson power divider circuit was developed in the 1960s by electronics engineering Ernest Wilkinson.
Rabia, please
Buradayım.
change your, yes, but you have to change your page on your laptop or anything else screen. Please.
Now I can change, but will you see me?
We are seeing the first page only.
1 minute. Did you see me?
Again, first page. Yes, content. Yes, yes, we are seeing now. Okay.
Okay.
That's okay. Okay.
Okay.
Thank you.
Okay. Nerede kalmıştım? As seen in the figure, the Wilkinson power divider or combiner uses quarter wave transformers to split the input signal to provide two output signals that are in phase with each other. The resistance between the two output ports allows the two outputs to match while providing isolation. The resistor does not dissipate any power, and as a result, the Wilkinson power divider could theoretically be lossless. There are some losses in practice, but they are generally low. And advantages of Wilkinson power divider, it can be easily implemented on the PCB. Low loss, high isolation between output ports. Disadvantages of this circuit, at higher frequencies, the size of the circuit elements increases, insulation resistant problem, low power applications, and use at low frequencies. Other application, insulation resistant layout problem. The major disadvantage of the Wilkinson power divider is that it depends on the internal resistors for good isolation. In high frequency, high power applications, as the size of the structure decreases and the size of the resistor increases, placing the resistor in this region creates a placement problem for Wilkinson power dividers. To get rid of these disadvantages, Yucel power combiner was used. Ulrich Yucel introduced his work in 1975 with the original name a new N-way power divider or combiner suitable for high power applications. Yucel power divider circuits have low loss, high isolation between the outputs, in addition to the features of the being able to be used at high powers thanks to insulation loads, easy to implement geometry, and easy to observe the imbalances in the output gates. As seen in the figure, it combines the input signals from port 2 and port 3 and forwards it to the output port, port 1. And 2 of the 5 ports of an ideal Yucel power combiner are terminated with 50 ohm resistors. The presence of grounded resistors have increased thermal efficiency by providing a pathway for heat conduction and does not limit power handling capacity. This feature is main advantage of the structure. Advantages of Yucel power dividers. The power holding capacity of the isolation resistors is quite high. The biggest advantage of Yucel power splitter is power usage. Ability to monitor imbalance in output ports, easily implementable geometry, and they are used as power dividers at the kilowatt level. Disadvantages of the circuit, bandwidth, and in terms of design, it takes up more space than Wilkinson power dividers. Why Yucel power divider? Because good results in high power applications, high frequency, external insulation resistance advantage, and high power capacity. We used RT5870 as the electric base. Our reason for using high resistance to moisture and radiation, low loss in high frequency application, the dielectric constant remains constant throughout the material, and the variation of the dielectric constant with temperature is very low. And now the schematic of the Yucel power divider circuit designed on AVR microwave office is shown in the graph. And a Yucel power divider with 2.5 gigahertz center frequency and 40 fractional bandwidth was designed for use in high frequency, high power circuits. And the bandwidth is between 2.2 and 2.8. In addition, RT5870 dielectric base features are the electric constant of this 2.33, the electric thickness of this 0.787 millimeter, copper thickness of this 0.035 millimeter, loss tangent of this 0.0005. Yucel power divider simulations are shown in the amplifier circuit design throughout the AVR microwave office program. Circuit simulation is done on the left, and electromagnetic simulation of the design circuit is shown on the right. The amplitude imbalance of the circuit is 0.00 387 dB, and fuzz balance is 0.102 degrees. The fact that they are two small bots, while for the circuit they are designed for. Comparison of S parameters obtained as a result of circuits and electromagnetic simulation is shown in the graph. The result is as expected. And the circuit designed on the AVR microwave office program was also designed with the Altium designer. Thus, the PCB of the circuit is formed. The resistor used in this project is this resistor. Our reason for using it is a silver material based 50 ohm resistor with 20 watt power capacity and frequency matching. Although this resistor has these dimensions, it has a high power capacity. The fact that its frequency is in the desired range is one of the reasons we use these brands. The circuit whose PCB was created on Altium Designer was produced and printed. Post-production resistors have been soldered. SMA connectors are embedded. The final state of the circuit is as shown in the figure. The measurements were carried out with the ZYA-50 circuit analyzer at TÜBİTAK National Metrology Institute, RF and Microwave Laboratory. As seen in the graph, we measured several S parameters such as S11, S21, S31, S32, S22, and S33. The measurements show us the simulation and measurement results are compatible with each other. Over the 2.2 and 2.8 gigahertz band, S11 is lower than minus 20 dB, and insertion losses of every port is nearly minus 3.4 dB. Results in this study, a two-way power combiner is designed to operate with very low loss in the 2.2 and 2.8 gigahertz frequency bandwidths, 25 fractional bandwidths. Isolation terminations have been added so that they can operate safely when 20 watt power is applied to their inputs. After electromagnetic and circuit simulations, it has been ensured that the fuzz and amplitude imbalance between the ports is low. And according to the electromagnetic and circuit simulation results, it's seen that the Yucel power combiner designed has 0.2 dB insertion loss, 0.07 dB amplitude imbalance, and 1 degree fuzz imbalance in the 2.2 and 2.8 gigahertz bands. As a result of the fabrication, the insertion loss of the circuit is at most 0.2 in the 2.2 and 2.8 gigahertz bands. The amplitude imbalance is at most 0.1 dB, and fuzz imbalance is 1 degree. Thank you for listening.
Thank you very much. Is there any question? Do you have any question? Okay. Can I ask a simple question? Mm-hmm. Did you say something about the heating of conductors and resistors due to high power transmission or division? This will be a problem for us. Okay.
Yes, okay, but we used these resistors because we want the power is 20 watts, because we want to see that our resolutions, our measurements, what happened, and these resistors of frequency is desired range is one of the reasons, and we use this brand. But we want to try this.
Mhm. Okay, thank you, Rabia, for your very interesting and very good presentation.
Thank you.
Okay, thank you. Okay, the last speech is low-cost carbon-based electromagnetic shielding material design at X and Q bands for electronics fabric and variable equipment. Okay, Zeynep Ertekin is the speaker of this presentation. Okay, Zeynep. Yes. Can you open your microphone, please? Your voice.
All right.
Yeah, that's okay. Okay, can you locate your presentation to your screen and then share to us? Nice, okay, it's coming.
Can you see my full screen?
We are seeing your screen, but that's okay. Now we are seeing.
All right. Hello,
Okay,
everybody. This is Zeynep from Yaşar University. I'm a PhD student and a research assistant at the same time at Yaşar University. My advisor is Professor Dr. Mustafa Seçmen. And my advisor, Professor Mustafa Seçmen, and another associated professor from 9 Eylül University, Mustafa Erol, together designed an electromagnetic interference shielding material applicable at X and Q bands, especially for electronics and variable equipment like occupational safety, hazard vests or gloves, etc. Today, I would like to introduce what we have done so far. During the presentation, I'm going to give you a few background literature information about this approach, how we prepared the shielding materials, the measurement setup we used, and how we prepared the test samples, and finally, our results with a little discussion and conclusion part. Well, electromagnetic interference is something unwanted. When electromagnetic waves encounter with each other, some unwanted interference happens. And this is important, especially for electronic applications, in a more basic sense with the military defense and maybe aerospace studies. Almost every government and every army have their own EMI shielding standards. This own standards make this topic very special, actually. In the literature, there are two basic approaches in order to overcome the EMI shielding. One is the reflection-based approach, and the other one is the absorption-based approach. Can you see my laser on the screen?
Yes, we are seeing.
All right. For the reflection-based shielding, when there is an incoming electromagnetic wave, if we can block this incoming electromagnetic wave, this is called as reflection-based shielding. There is another method. If you prevent the transmission along with the reflection, this is called as absorption-based EMI shielding. Reflection-based shielding is mostly done with conductors. They have high reflectance and low transmittance. And absorption-based ones are done by dielectric lossy materials along with magnetic lossy materials. As I told before in the previous slide, this is mostly done by metals until like late 19th or so. But in the very early beginning of 2000s, researchers proposed another method. They thought that the metals were quite heavy and they had thermal conductivity issues and durability issues. So they wanted to create something lighter. So they proposed to turn polymers, simple polymers, into EMI shielding materials. By how? By two different approaches. One approach is to embed, fill these polymers by conductive materials like carbon derivatives. This could be carbon black, carbon nanotubes, or etc., any of them. Another approach is to selecting intrinsically conductive polymers in order to obtain satisfactory EMI shielding. In the literature, you can see dozens of examples. Actually, 2 years ago, me and my professors, we did something with this polymer PVDF, but this year we tried something different, and I would like to explain that one. This year we did something new, something not given in the literature to the best of our knowledge. We are the first team done this. We used screen printing ink. You might ask the question, what is screen printing ink? Ink is nothing but this ink on the t-shirt. The white ink, the red ink, the blue ink, it doesn't matter. What we used was this ink as polymer matrix, and we embedded electrically conductive particles into this polymer matrix. The polymer matrix includes these chemicals: polyacrylic acid, sodium salt, ethylene glycol, titanium dioxide, and water. This was the base of the polymer matrix. And in the previous slides I'm going to show you, we embedded conductive particles of carbon black and graphite. Here you can see the material safety data sheet of the proposed inks polymer matrices properties. The manufacturer was Turkish. It was purchased from Uras Kimya. So the MSDS data sheets, material safety data sheets, are also in Turkish. Excuse me for this, but you can see any kind of information in here, like labeling, classification, national coding of CAS or EC numbers. I added this in order to ensure you that what is inside the ink. Now I would like to give some information about how we prepared the composites. In the figure, you see some samples, some of our samples. These are 100% compatible with the waveguide structures, considering the hollow dimensions of waveguides. As you can see in the picture, we embedded carbon black particles and graphite particles into the matrix, and we filled the spacers, holders, by the proposed material. As you can see in the picture, they are in an oven. It's because the ink matrix included deionized water, and for better results, we need to get rid of the water. In order to let the vaporization occur, we left them in a drying oven at 85 degrees for 8 hours. And after this vaporization, we also left them in the same drying oven at 250 degrees for 12 hours for curing. And curing is a process in order to fix the physical and chemical properties of the proposed materials. In this study, we investigated the shielding properties of screen printing ink itself, which was a polymer matrix, screen printing ink combined with carbon black particles, screen printing ink combined with carbon black and graphite particles with the same amounts, with the same ratio, and we doubled the ratio of graphite particles. Actually, we have so many samples, but since we have very limited time and page, we excluded most of them. Here you can see our measurement setup and test samples. This is the vector network analyzer we used with the 2 ports. For X-band and Q-band, we used separate SMA to waveguide adapters with the given following dimensions. The thickness was set to 3 millimeters in order to satisfy the lambda 0/4 criteria for both of the frequencies. And as you can see in the picture below, we have prepared lots of samples. Let me explain a few of them to you. Please give a look at the rightmost upper corner of the second picture. I'm showing with the laser. You can see this is white. This is white because this is the polymer matrix itself without any conductive fillers. The rest of them, the rest of the samples include different amounts and different types of conductive fillers. And we have checked the EMI shielding properties of all of these samples during this study. Well, it is very well known that shielding efficiency of a material, a very well-known material like copper, gold, or aluminum can be computed by some formulas given in the literature. If the intrinsic properties, if the constitutive parameters like conductivity, complex permittivity, and permeability are known. However, since the material we designed is something quite unique and new, we didn't have an option like this. So we kind of did reverse engineering by using scattering parameters S11, S21, and the reflection and transmission coefficients. We also extracted the complex permittivity and permeability of the offered materials, which I'm going to explain in the following slides. Now I would like to explain our results. For all of the graphics I'm going to show you, the thickness was set to 3 millimeters. We also studied for 2 and 1, but of course, due to limitation, we excluded them. But even for 1 millimeter, we obtained at least 10 or 11 dB shielding efficiency, I would like to explain. The blue curves represent this polymer matrix itself. The orange curve represents polymer matrix, also including carbon black particles. The yellow curve represents carbon black and graphite together. And finally, the purple curve represents carbon black and graphite together embedded, but the ratio of graphite is 2 times greater than carbon black. As we expected, the polymer matrix itself behaved like a good dielectric with low loss properties. Since both the S11 and S21 parameters are low, it behaved like almost air. However, when we embedded conductive fillers of carbon black and graphite, things changed and it started to behave like it is something conductive. It behaved like a metal and it prevented the transmission of electromagnetic wave to the second port. As we can see, the scattering parameter 2.1, the transmission parameter decreased remarkably from almost 2.5 dB to the level of 15, 16 decibels or so. And when we also added graphite particles, S21 parameter also decreased considerably in here. And finally, when we doubled the ratio of graphite particles with respect to the carbon black particles, what we obtained was nothing but a satisfactory shielding result of 30 dB minimum along the frequency band. And these data were collected for X band. We're also gonna look for the behavior at the Q band, the following frequency range. Again, blue curve represents the screen printing ink matrix, polymer matrix. Orange one represents carbon black, yellow carbon graphite, purple carbon graphite, but the amount of graphite this time is 2 times greater than carbon black. Of course, there is no change in the behavior of the screen printing ink matrix, and there is gradual increase of better shielding property when we added carbon black and graphite particles. And we can see that the dominant contribution is from graphite. It's because when we increase the amount of graphite particles in the proposed material, we obtain better shielding efficiency. And from literature, we know that carbon black, graphite, and some other carbon derivatives are quite good conductors, but as we are familiar with, at high frequencies, most of the things change. We also kind of proved that they represent conductive behavior in high frequencies at least 28 dB when they're together along the Q frequency range for scattering parameter 2.1. It's like 99.99% of the incoming electromagnetic wave was blocked by the material we designed, as you can see with the purple curve in here. Now I would like to talk about the reverse engineering part. In the previous slides, as I said before, if the constitutive parameters of conductivity, permittivity, permeability, etc. are known, we can obtain shielding efficiency. But we didn't know any of them. It's because the material we designed was new and unique. We did reverse engineering by using scattering parameters S11, 21, 12, 22, and coefficients of reflection and transmission. We have computed complex permittivity and permeability by a very well-known famous approach proposed by Weir in the literature. And this method is known as Nicholson-Ross-Weir algorithm. By using these mathematical expressions, I coded the algorithm in MATLAB, and we extracted the complex permittivity, relative complex permittivity and permeability of the design materials. Here we see the Bayer screen printing ink matrix constitutive parameters, complex permittivity and permeability. As you can see in the slide, it behaved like a good dielectric, a low-loss dielectric material, and imaginary lossy parts are close to zero. However, this is valid for, of course, this is valid for two frequency ranges, but in the next slide, I'm going to show you the one when we add the conductive fillers of carbon black and graphite. When we added carbon black and graphite into this proposed matrix, this time imaginary part, I mean the lossy part, increased considerably. So this actually is like a cross-check of the scattering parameters. The difference between the real part and imaginary part increased, and this states nothing but a little bit conductive behavior of the design material as far as we're concerned. Here is a comparison table of the related studies in the literature with ours. In the literature, probably due to the properties of vector network analyzers, most of the studies investigate the shielding properties or absorption properties within one frequency range, but we try to investigate for X band and KU band together. And as you can see, the comparison, we obtained satisfying EMI shielding results in the table with respect to the other studies in the literature. And you can see some of the references. I did not add all of them. It's because it was like more than 30 or 40 references. In conclusion, to the best of our knowledge, for the first time in the literature, this screen printing ink matrix was used as polymer matrix. Even though screen printing ink, screen printing method is used as a manufacturing technique, the ink itself has been used as a polymer for the first time. The great news, it's quite cheap. It is quite cheap, especially with respect to the chemicals, polymers, sold by American companies, British companies, German companies. This is something very cheap, something very reachable for everybody. Another news is it is compatible with the conductive fillers of carbon black and graphite. At X band and KU band, we obtained satisfactory shielding, EMI shielding results, like 28 dB minimum during the band and 30 dB minimum during the band. And this proposed material can be used to overcome EMI shielding problems in radar or microwave applications, and also can be used as an occupational safety and hazard vest or glove, like in those kinds of applications. I would like to thank my university. This study and research was supported by a scientific research project number 99 from Yaşar University Scientific Council. And also this research was supported by TÜBİTAK National PhD Scholarship Program within the area of priority fields for Turkey. And I would like to express my profound appreciation to my roommate, Ceyhan Türkmen, who lost his life on the 15th of November this year. He taught me how to use the vector network analyzer, how to deal with the calibration of the waveguides and everything. We have studied so much together until like 10 days ago or so. I would like to express my deepest and profound thanks to my late roommate, Ceyhan Türkmen. Thank you for listening. I would be more than happy if you have any questions.
Okay, thank you very much. Also, we are sorry for your friend also. How can I say anything else? I don't know. Okay, do you have any question about this presentation?
Can you hear me?
Yes, please.
Okay.
Yes, I have a question I written to
Yes, we are hearing you.
chat room and also the chair answered. Thank you for your answer. And do you have any limits? Actually, the limits for frequency range.
All
Actually,
right,
you
Nicholson-Weir-Ross method.
yes.
All right, in the literature, there is no limit, but in his paper, I can share with you the Weir's paper. Weir studied this algorithm for X band, but as far as I'm concerned, there is no limitation.
Okay. Did you add this paper to your references?
This paper, of course, yes, Weir's
okay.
paper, of course I added.
Okay, thank you.
And that's all.
Okay. Is there any other question? No. Okay. Zeynep, is it a flexible type shielding? Flexible or solid one?
Well, this is solid, but 2 years ago, again with the same team, we did something flexible based upon another polymer. It was relatively more expensive, but this is definitely cheaper. But there are ways to make it flexible. There are some chemicals called as dopants, dope materials. And when we add these materials, the flexibility increases enormously. It is solid, but we can make it flexible.
Okay, very nice. Okay. Okay. Thank you very much for your presentation also again. I want to close this session. Thanks to attendances and speakers for all. Okay, thank you. Bye-bye.
Thank you.
Bye-bye.
See you.
Much.